Hi, and welcome to this presentation of parkoptimizer, an add-on module to WinSim. Parkoptimizer is a tool that will help you maximize your wind farm profitability by optimizing the wind farm layout, locating turbines in areas with ISE-compliant wind conditions, and helping you determine the right level of investment by identifying the optimal number of turbines within the wind farm site. So, let's see what parkoptimizer can do. parkoptimizer uses results from WinSim CFD project, so in order to start, we need to find an interesting project to work with. The projects are found by clicking the Select button in the menu at the top. You select the WinSim project file to open a new project. The program will now read data from the WinSim project, and the terrain will soon appear in the area map to the right. In order to run parkoptimizer, you will need a time series from a map mast within the area, a long-term corrected WRG file, power curves for the turbines you want to consider, and wind flow variables at different heights extracted from the WinSim project. Depending on what hub height and rotor diameter your turbines will have, you can determine the calculation heights in the data specification menu. The simulation height should be the hub height of the turbines, and we recommend that the shear deviation is approximately 1/3 of the total rotor diameter. Here you can also choose how many sectors that you want to do calculations for, depending on your settings in the WinSim project. In this case, we have run wind fields for 12 sectors. parkoptimizer generates different results files. These are automatically stored in a new parkoptimizer folder in your WinSim project. You can choose to store them somewhere else by selecting a different results directory under the General tab. The wind farm needs to be located within a park area. This can be imported either as a shapefile or as a PGN file, or you can choose to draw it yourself by clicking the Draw button. In this case, we will import the park area from a shapefile. As you can see now, the park area is depicted on the area map. The next step is to calculate an energy map for the wind farm. This is done under the Energy Map tab that you will find in the tab strip menu. In order to make an energy map, you will need a wind resource file in WRG format and a power curve for the turbine you want to consider. The WRG file can be generated by WinSim, and you will find it in the report folder in the layout where it was created. In this case, we want to use a Siemens 93 turbine. You will need a PWS file to import a power curve. Now everything is ready, and we press Calculate Energy Map to do the calculation. When the energy map has been calculated, it is stored as a CSV file in the results directory. This file can be opened later on, so you do not have to do the calculation every time. For more details, a figure can be opened and investigated. In this case, the wind resource looks good. Moving on to the constraints, we will now start to investigate the wind quality in the park area. parkoptimizer will evaluate wind quality against the constraints that are selected in the IC Constraints menu. As you can see here, terrain inclination is also included as a constraint. In this case, we are regarding a Class 2A turbine, so the turbulence can be set to 18%. The extreme speed should be 42.5 meters per second. All areas that violate these constraints will be excluded for turbine placement, so be careful not to exclude areas that might be viable for turbine locations. By selecting the different criteria, you can decide for yourself what you want to consider. Both turbulence and extreme wind speed should be calibrated against measurements. TWS files can be selected in the Setup menu. In this case, our measurement period is too short for extreme wind speed to be considered. By pressing the Extract button, the calculations will start. The resulting map shows us that the wind conditions are violating the constraints in rather large areas. Turbines will have to be located in the white areas in order for the layout to be compliant with our constraints. You can save and open previously made exclusion maps. The file will also be saved as a GRD file that can be opened in different tools. If you have other constraints to consider, these can be drawn or imported as shape or PGN files. In this case, there are several small lakes within the wind farm area. By importing these as shape files, we can be certain that no turbines will be located on water. We are now ready to create our layouts. By moving on to the Layout tab, we can specify the settings for a layout optimization. You can choose to generate a single layout if the total number of turbines is fixed. However, if you want to investigate the economic impact of changing your wind farm size, a multiple layout should be created. In this case, we want to optimize for layouts from 1 to 10 turbines. We recommend that at least 4 rotor diameters are chosen as the minimum distance between the turbines. The rotor diameter and weight decay constant has to be specified before the optimization is started. As the optimization algorithm is non-formal, improvements can be made by running the optimization several times. This can take some time depending on the size of the wind farm and the number of turbines. If you have made an optimization already, you can open the results by clicking the Open Layout button. The layouts are stored under the Opt-out folder. Different runs are stored in different folders, and the improvement for each run is reported in a log file. In this case, 2 runs have been made, and we open the last layout. By opening the CSV file, the program will automatically open all layouts ranging from 1 turbine to 10 turbines. If you want to investigate the layout, a detailed figure can be made by clicking the Figure button. A figure will then appear, and by using the Layout GUI, it can be customized to fit your needs. A background map can be imported either as a JPEG or a GeoTIFF image. The resulting figure can be exported to a Google Earth KML file, and the constraints, wind resource map, and the layout can be investigated in a 3D environment. It is also possible to generate a detailed IEC report. This report is stored as a text file, and it documents all files and settings used in the parkoptimizer project. The IEC constraints are reported for all turbines, both aggregated and sector-wise. As it can be seen in this case, the effective turbulence is a bit high for some of the turbines. Using parkoptimizer, you can optimize your layout with regard to effective turbulence. Tick the Use Effective Turbulence mark and do a new optimization. You will need to specify a TWS file for calibrating the modeled turbulence. Moving on to the last tab, we will evaluate the wind farm profitability. As you understand, as you put more turbines into a site, the marginal energy yield will be reduced. This is due to the fact that the last turbine has to be placed in a less favorable position, and that it will reduce the output of the other turbines due to the wake effects. By adding financial parameters as expected prices and cost estimates, the optimal number of turbines can be identified by pressing the Calculate button here. Using the parameters I have added here, you can see that the net present value of the wind farm is reduced when more than 8 turbines are located in the park area. I will not go into details here, but you are welcome to contact WinSim for a more detailed description of the methodology. If you find this tool interesting, please contact WinSim at www.winsim.com for an offer.